Hi, everyone. Thank you so much for joining us for tonight's Southern Sky live stream. It is cloudy here in Sydney, so we're broadcasting our monthly astronomy program tonight from the Powerhouse Museum. The Museum of Applied Arts and Sciences acknowledges Australia's First Nations people as the traditional owners and custodians of this land and pays respect to elders past and present, and through them to all Aboriginal and Torres Strait Islander people. My name is Catherine Poltz. I'm the science producer at the Powerhouse and Sydney Observatory. We have a great program tonight with Professor Lisa Harvey-Smith, who will be exploring the evolution of galaxies and the science behind the visible, spiral, merging, and elliptical galaxies we'll view. Everything that we're discussing tonight is visible in the June winter night sky. However, because it's cloudy, we do not have live telescope footage, but we do have some spectacular images of the targets we are discussing. So, as always, we hope our program grows your appreciation for the beauty of our southern sky and inspires you to go outside and look up. We will also be taking your questions throughout the program, so please write them into the comment section and tell us where in the world and where in Australia you're joining us from. I'll now introduce Lisa. Professor Lisa Harvey-Smith is an award-winning astrophysicist and the Australian government's Women in STEM ambassador. Lisa's research investigates the birth and death of stars, colliding galaxies, and cosmic magnetic fields. She's the author of many books, including When Galaxies Collide, the best-selling children's book Under the Stars, Astrophysics for Bedtime, and The Secret Life of Stars. This year, she also has 2 new releases, the little book Big Universe and Aliens and Other Worlds, which will launch in September 2021. Welcome, Lisa.
Thanks so much, Catherine. Great to see everyone again. I'm afraid it is cloudy down the eastern part of Australia, but we will persevere because we will have invisible eyes tonight. We're going to be looking through the clouds through billions of years of history, and I hope you're going to enjoy it as much as I always do to be here at Sydney Observatory. I'd first like to acknowledge traditional owners of all the lands on which we're meeting tonight across this great southern continent, and pay my respects to elders past and present. This is a beautiful, beautiful night, whatever night it is, to be thinking about the stars, whether or not it's raining, whether you have clear skies, perhaps somewhere else in the country. But I want to talk this evening about the galaxies. And these are things that, whether or not it's cloudy, we can't really see very often with the naked eye. So we're going to start with something we can see and then move to further, deeper and more exciting objects that tell us more about the history of our universe. The galaxies are really, in many ways, the building blocks of our universe. If you're building a house, you might choose to use bricks as your material, and you build them up together and you create giant structures that we can live in. The universe has evolved, of course, under the influence of the physical laws of nature, for example, gravity. And gravity has really molded objects through the influence of dark matter, which is the dominant component of our universe. It's mysterious stuff. We don't even know what it is. And through that, the gravitational forces have pulled everything together since the time of the Big Bang and created beautiful structures. They're not houses, but they are galaxies. They are the home of us, our planet, our solar system, our star system. And they are made up of normally hundreds of millions or even billions of stars, gas, and other materials. So really, they are the building blocks of everything. They are extremely big. There are about 2 trillion of them, and each one is, let's say, an average one the size of our Milky Way, contains about 100 billion stars and is 100,000 light years across. So you might be wondering, can I imagine how big 100,000 light years is? How big is the Milky Way? Well, when we look across space to the other side of our galaxy, into the most distant stars in our galaxy, we're seeing the light that was emitted 100,000 years ago, when our ancestor species, Homo erectus, were walking the Earth, when Neanderthals were walking the Earth, when woolly mammoths were crunching their way through the wintry crisp leaves on the plains and steppes of the land that's changed so much since then. So, this is a really, really long way away and a really long time ago that we're studying. And galaxies don't happen alone. They are actually found in clusters. And galaxy clusters are enormous, and they have dozens to hundreds of members. Now, ours is no different. We live in a local group of galaxies of about 50 members, which is then part of a larger cluster of many thousands of members. So those are called clusters and superclusters of galaxies. Now, for the distances across these large reaches of space, it's even harder to imagine the sizes. So if you imagine the distance between us in this galaxy cluster and the next galaxy cluster, the closest one to us, light traveling at 300,000 kilometers per second would take the same time as the time between when T-Rex, Tyrannosaurus Rex, the big dinosaur, went extinct, and the present day. So that's just showing us how much history we're looking through when we look at the stars and when we look across the galaxies. So since galaxies are bound into these groups and clusters by gravity, the universal force that attracts things together, it's not actually too surprising that galaxies can also get tangled up. And actually, interactions between galaxies, collisions between galaxies are very common. And the sort of shape and size of a galaxy and what it looks like, its so-called morphology, tells us a lot about the history of collisions that have happened. So in other words, we can, just like if you walk around, look at a bunch of people, you can guess what kind of life they've had, how old they might be. You can also look at galaxies and you can see how old and withered they look, how many wrinkles they have. And we can do this as astronomers to study the history of the universe and how the galaxies may have interacted, emerged in the past. So, for example, if a galaxy evolves in isolation and doesn't have many collisions between it and other galaxies, then it's likely to form a spiral galaxy like the Milky Way. Now, spiral galaxies may have had a few interactions with maybe small dwarf galaxies, and that may have indeed created the spiral arm structure that we see. We're not too sure about that's actually the case, but that's one of the leading theories. But these spiral galaxies like the Milky Way, where we live, have plenty of stars left. They're still forming stars. There's lots of gas lying around in the galaxy, and that gas is still being pulled together by gravity to create new stars. So it's kind of like a sort of busy, active, booming kind of galaxy. On the other hand, you look at some galaxies in our universe, especially large elliptical galaxies, and elliptical kind of means like a sort of a squished, long, round shape like a football. That can result from multiple mergers. So collisions between galaxies have happened again and again and again through the galaxy's history since it was born, 13 billion years ago towards the start of the universe. So in those galaxies, new stars aren't forming because there's no gas left. And all the star formation has happened. So you just got a bunch of old stars hanging out. It's a bit like a retirement home. So tonight, I'm going to take you on a tour through the many different types of galaxies and the different stages of galaxy evolution that we can see in our night sky. And first is one of my favorite objects to look at with the naked eye. And it is, of course, the Small Magellanic Cloud. Let's take a look. You can see this beautiful object, as I say, with the unaided eye. It looks, with the regular eye, like a bit of a smudge in the night sky. You look up in the constellation of Tucana, the toucan, and you look up and you see in a beautiful clear black sky this kind of little cloudy smudge, almost like someone's been eating a bag of chips and then touched their iPhone screen. This sort of greasy smudge in the sky. Now it lies about 190,000 light years away from Earth, which is very close compared to most galaxies. It's one of the closest objects to us. And it contains about 7 billion stars, or the mass of 7 billion suns equivalent. So there's a lot of stars in there, but only a small proportion of the size of our Milky Way. But because it's so close, it's easily visible in the night sky and covers a big area of the sky, about 70 times the size of the full moon. Now, it forms a pair with the Large Magellanic Cloud, which we'll see in a minute. But we'll stay with the Small Magellanic Cloud for a second because there's some really interesting features that we can see. There's a bridge of gas connecting these Magellanic Clouds. They're both small galaxies. And this is the tidal interaction. In other words, gravity is actually kind of clamping the two together, and they are moving in space and interacting. Their gas is streaming from one to the other, and they're creating a kind of a comet's tail in space, which is really fantastic. And we can see this tail with radio telescopes. And that indicates that the two galaxies have been gravitationally bound together for a long time. Now, the Magellanic Clouds were formed around the time as the Milky Way, so about 13 billion years ago or so. And they are captured by the gravity of the Milky Way in some way. So they're kind of spinning around and around. Now, you can see in this galaxy a lot of red areas, which are areas of star formation. And you can also see on the right-hand side of the image a really amazing kind of spherical body. It looks a bit like a swarm of bees. And I just wanted to mention that because it's this beautiful globular cluster in our Milky Way. It's actually in the foreground of the image. It's much closer to us. But I wanted to show you an image from the observatory telescopes, which was taken a little while ago before it clouded up in Sydney. But this is just a beautiful image taken from the East Dome telescope at Sydney Observatory of 47 Tucani, this wonderful globular cluster. These are very, very compact, tightly packed clusters of stars in our galaxy. And they live not in the disk, in the plane where we live in the galaxy. They live up in the halo above and below the disk. So there are lots and lots of these, about 150 to 300 estimated number of globular clusters in our galaxy. And they're quite beautiful objects to see. And you can see this one through a pair of binoculars if you're ever in the area. Just a note on that, if you do want to find these objects in the night sky, get your smartphone, if you have access to one, and download an app of the night sky. So some of them are called things like Sky View, Sky Guide. There are quite a few of them. Some are free and some you might pay a couple of dollars, but you can then point your phone up at the night sky anytime, day or night, and you can see what stars are up there. You can type the names of these objects in and actually locate where they are, so you can see them. So that's something fun you can do when the sky clears up, or if you've got a lovely clear night tonight. So that was a small Magellanic Cloud. Let's look at the large Magellanic Cloud. This is also visible with the naked eye from Australia. And it looks, again, like a greasy smudge in the sky. It's a luminous patch of light about 5 degrees across. And just for context, the full moon is half a degree across, so about 25 times that. And you'll find it in the constellations of Mensa and Dorado. It's kind of so big that it crosses the boundary of those constellations. So it's quite close to the small Magellanic Cloud in the sky. Look roughly south. It's not actually south, but that kind of direction. And you'll see it there. This one is larger, hence the name. It's 14,000 light years in diameter and lies about 160,000 light years from Earth. So the type of galaxies is sometimes called an irregular barred spiral galaxy. So you can sort of imagine when we're looking at this galaxy, there's a bit of a line across like this. It's kind of a straight line. Now I'm doing that. I'm backwards, so I've got to do it that way. So there's that kind of angle that you can see. And it almost makes a straight line. So that's called a bar in a galaxy. Our galaxy has a bar across the center, and then it has its spiral arms. Now this one has a bar and just one spiral arm. And we think that it was disrupted by tidal interactions by the small Magellanic Cloud and our Milky Way. So essentially, it had a bit of a regular shape, and then these interactions and gravity sort of squished and smudged and smooched the galaxy and created this irregular shape. It's trying hard, it's trying its best to be a spiral galaxy, but it just gets interrupted too often. Now, the Large Magellanic Cloud's got about 15 billion stars. It's not too small. It's pretty impressive, and it's actually home to a really cool area of star formation, the most spectacular region of star formation in our entire local group of galaxies, and it's called the Tarantula Nebula. So I want you to look sort of top left, just above the bar, the pink line, and you can see this kind of cool object that looks a bit like a crab or a spider. if you look at the letter D in the word cloud, go down and slightly to the right, and you can see that greeny, orangey, crab-looking object. Now that is called the Tarantula Nebula. You can imagine why it's called that. It seems like a very spidery shape. It's actually an H2 region, technical term, which means hydrogen that is ionized. So hydrogen atoms of gas in this region have been smashed by ultraviolet light from really, really hot young stars that are forming in that region. Now, the region is a giant stellar nursery, essentially. So these huge hot stars are forming. They're ionizing the region, and they are making it glow very bright. So it's actually so bright that if it was as close to Earth as the Orion Nebula, it would actually cast a visible shadow. It would be so bright in our night sky. And luckily it isn't, because we wouldn't see many stars. We don't want these bright things to be too close to us. That would also obviously mean that the stars, as they grow up, would start to, generate supernovae, which is also not a good thing to be close to us. So 2 reasons to be grateful we don't live in a large Magellanic Cloud. But this is the most active region of star formation in the local group, as I said. And it's really cool because right inside there's a cluster of stars, and it contains the most massive and luminous star known, which is called R136A1, which I always forget. It's 215 times the mass of our sun. That is absolutely just phenomenal. It's got more than 6 million times the luminosity of our sun, and this is a single star, and it's one of the hottest stars. Its surface temperature is over 45,000 degrees. That's not the core temperature, which will be many millions of degrees, but that's just the surface temperature, 46,000 degrees Kelvin. By comparison, our sun is only 5,800 degrees on the surface. So it's bright, it's hot, it's luminous. When it runs out of hydrogen fuel, which it's currently fusing at an incredible rate, it will actually explode as a supernova, and probably something which our ancestors will see with the naked eye, a very, very bright supernova within a few million years. And at the core of the supernova will be left a tiny remnant of material that will no longer be burning hydrogen and hot enough to sort of create outward pressure to counteract the force of gravity. So the force of gravity will win. When the supernova happens, the outer layers of the star will expand into space with a giant shockwave, and the central core of the star will suddenly collapse to form a black hole. So all of that is awaiting this wonderful Tarantula Nebula and the stars inside of it, and particularly R136A1, which is just an incredible, hefty star. Something like this actually happened not too long ago, in 1987, on the outskirts of the Tarantula Nebula. What happened was that people were just minding their own business, 1987, wearing slightly too baggy jeans, and they were walking around, and they just suddenly saw a new star in the night sky. And there were also gamma ray detectors, which were neutrino detectors as well. Neutrino detectors detecting these tiny, tiny particles from space. They're often buried in mines and underground. And they suddenly saw a flash of neutrinos, these particles that are thought to be caused only by very, very high energy events like supernovae. So first of all, the neutrino detectors went ping. Second of all, a new star appeared in our night sky, and suddenly there was this supernova 1987A, the first supernova seen in that year that was visible in the night sky. Some of you may have seen it. Some of you who are enthusiasts of astronomy and may have your own telescopes, may have been to Sydney Observatory or other observatories to see this star. But it reached peak brightness in May of that year at an apparent magnitude of about 3. And magnitude 3 objects are pretty bright. They're, like regular stars that you can see from a city. So, it was a very, very significant event. And it was very significant for a couple of reasons. It was great for people to see this event, this star exploding in a nearby galaxy, but It was also useful because it was the first supernova close to us. It was close enough to see with the naked eye since 1604, Kepler's supernova. So really it was the first since the advent of many modern techniques, such as observing the sky with telescopes and spectroscopy and studying the chemistry of space and understanding particle physics. So it was the first example where we could test our theories of supernova explosions. That was a very, very good thing. So over the years, since 1987, astronomers have been looking at the gas expanding into space, creating very narrow rings around the star that exploded as the shockwave expands into space. Very, very cool subject. So we're going to look next at a galaxy which used to be called something quite beautiful, the Sleeping Beauty galaxy. But unfortunately, a more sinister name stuck, and we now call it the Black Eye Galaxy, or Messier 64. So let's take a look at the Black Eye Galaxy and see why. You can probably obviously see why it's called that. It's easily identified by this incredible band of absorbing dust, which is partially obscuring its bright nucleus. So the galaxy has a nucleus, the stars towards the center, they're closer together. They're slightly older stars, but it's a very bright region that contains a lot of gas as well. And then the spiral arms, they appear quite blue because the stars in the arms are quite young. That's where pressure waves or shock waves are generating new stars as the shock waves kind of crunch together the gas and help gravity along on its task of pulling gas together to make new stars. So the galaxy has a lot of this dark, obscuring dust, which gives it this kind of really interesting black eye appearance. And weirdly enough, when we measure the motion of the gas in the galaxy, normally a spiral galaxy will just have the gas all moving around in nearly circular motions in the same direction. But in this galaxy, the gas in the outer regions is actually rotating in completely the opposite direction from the gas and stars in its inner regions. So this really strange behavior can probably be attributed to a merger between the Black Eye Galaxy and a satellite galaxy over 1 billion years ago. So essentially what's happened is the galaxies have merged, and that's created a huge explosion of new stars. And then the stars have lived and died and generated the dust in space. And this dark dust with a lot of carbon in it is like coal dust. It's very black, and it absorbs the light from the stars. So what is happening? We've got a flurry of starbirth created by a pressure wave caused by galaxies colliding, creating an amazing bruised appearance on this galaxy with the inner part circling one way and the outer part the other. New form stars are blue and the older regions are red. Absolutely beautiful. So this galaxy is able to be seen in a moderate-sized telescope. It's got a magnitude of about 9.8, so not visible to the naked eye, but definitely spotted in Sydney Observatory's beautiful telescopes. So come along and see that sometime. Now, the next galaxy I wanted to show has also got a bit of a weird appearance because we like the oddballs here. So this galaxy is very cool looking, and you may have seen this image before. If you haven't, it is real. All of these images are real. And this galaxy is called the Sombrero Galaxy. And I think when you see it, you'll understand why. Now, galaxies don't point in any particular direction in space. They're, all pointing in pretty random directions. So most galaxies are sort of flattened into disks, and some are seen face on, and some are seen edge on. So this particular galaxy is seen edge on. And we can see, just like the Black Eye Galaxy, it has got this incredible band of dark dust. And this tells us about the history of the galaxy too. It lies in the constellation of Virgo, where we see a lot of galaxies because the Virgo cluster is where we hang out. And there are thousands of galaxies in this cluster. So lots and lots of things to see in the constellation of Virgo. This galaxy has a total mass of 800 billion suns and is around a third of the size of the Milky Way. So it's easy to see with a small telescope or binocular. But if you want to see a really cool image of the dark dust lane, nothing better than a big, big, juicy telescope like the ones you can see at the observatory or even the Hubble Space Telescope and the types that we see professional images from. So looking online, you're just going to get an incredible view. But there is nothing like seeing these beautiful galaxies with your own eyes. It's a wonderful feeling because it connects you to it. It makes you feel, connected and also inspires. I think it really takes my breath away every time I look through a telescope at these objects. Now, you might think this galaxy looks a little bit similar to the Milky Way, but edge on. But it's actually pretty different from the Milky Way. You'll notice that the color is fairly orangey, so it's not as blue as the Milky Way. And it's also got a very bright nucleus. So you can see that core, that glowing sort of orangey yellow gas in the middle. That's very, very prominent. And also very prominent is its dust lane. So the thing that makes it look special. And that dust lane is really quite unique. It almost looks like the rings of Saturn, I think. And the dust lane is chiefly made up of hydrogen gas and dust. And by dust, astronomers mean molecules in space that are joined together. So big molecules, they can be made of like carbon, hydrogen, oxygen, nitrogen. And that the conditions in outer space and the ultraviolet light enables chemical reactions to happen and create bigger molecules. You'll find things like methanol and ethanol, and you'll find water in space and lots of even bigger molecules too, many, many carbon chain molecules, and even the types of molecules that may start to form life in the future. So it's an interesting chemistry experiment looking up to the stars. The Sombrero Galaxy looks like a spiral from the side, but it's actually got more traits of an elliptical galaxy. It kind of looks like an elliptical galaxy has swallowed a spiral galaxy when you look at its motions. But it's really hard to imagine how that's happened because the spiral galaxy structure would have been destroyed by the collision. So the only way to understand this is really to think of it as two galaxies, one inside the other. And we don't actually yet understand the dynamics and the interactions that have caused that. So this galaxy is a mystery wrapped in an enigma, quite literally, actually. That's hard to say. It is hard to say, and it's hard to understand as well. So lots of mysteries with this galaxy, still studying its dynamics, its history, its chemistry, and the magnetic fields in the galaxy. Lots and lots to understand. This is why astronomers keep looking, because there are things like this, real oddities that happen in space that we don't understand. I wanted to go to the last galaxy before we take some questions. So start formulating some questions in your mind if you have anything that you think is interesting, you'd like to know more, or maybe we can discuss some of the subtleties of these images. But also, if you've ever observed these objects, share that. You can share it on the Facebook page afterwards, perhaps post some images. That would be really, really nice. It always is fun to see images that people have taken as well. But the last one before the Q&A starts, and then we'll have some more galaxies after that, is the Southern Pinwheel Galaxy. Now, Pinwheel is just beautiful because it's face on. We're seeing, not from the edge, we're seeing a galaxy face on, and it just looks like a beautiful octopus, I think. This one is truly spectacular. It's called M83 as well as the Southern Pinwheel. M means Messier. It's the name of a French astronomer, Charles Messier, who made a catalogue of fuzzy objects in the night sky in, I think, the 18th century. Now, that catalogue is now really useful for professional astronomers and amateurs alike to find our way through the night sky and find interesting objects. The reason he made the catalogue, by the way, was that he was a comet hunter and he wanted to quickly have a record of objects that weren't comets. So when he was looking around trying to find interesting fuzzy blobs, and he kept finding the same ones and going, no, that's not a comet, that's not a comet. So he had a catalogue made, and then he could discover his comets. Well done, Charles. But this galaxy, not a comet, is 15 million light years away. So very, very close to us, relatively speaking, in the local vicinity, according to the size of the universe, which is huge. You can see its features. It's a spiral galaxy. It's got a bit of a bar in the spiral, so a bit of a straight line across the middle of the galaxy. And there's beautiful spiral arms extending across the ends as well. So on the face of it, looks very much like the Milky Way. It's gorgeous. It's a stunning place, and lots of stars forming in the spiral arms. It has globular clusters in the outer regions. It's gorgeous. But actually, when we look closer, you can see a lot of pink regions. It's kind of pockmarked with pink regions. And there are a lot more of those than there are in our Milky Way. And what we see when we look with infrared telescopes, we can see stars forming inside dense dust and gas that we can't see with the naked eye or with optical telescopes. Because when we use different wavelengths, when we look at galaxies with, say, a radio telescope or an infrared telescope, we see things we don't see with normal light. So we see with infrared telescopes around 3,000 young star clusters in the galaxy, many of which are less than 5 million years old. So this is a really strong bursting starburst galaxy. In other words, it's a spiral galaxy where lots and lots of new stars are forming. And all that activity may well be the result of a collision with another galaxy. So this beautiful image captures hundreds of thousands of individual stars and thousands of star clusters and hundreds of supernova remnants. So the remnants of exploded stars. It's one of the brightest spiral galaxies in the night sky, and you can look at it with binoculars. So I very much recommend typing M83 into your star app that you either have now or you might download later, and take a look at this beautiful object with your binoculars. Now, we've looked at interacting galaxies, irregular galaxies, elliptical galaxies, black-eye galaxies, and more. There's still some more really, really cool ones to come. But for now, I'd like to pass back to Catherine, and we will do any of your questions.
Yeah, we have some really good questions coming through, and keep sending them through to us. But Lisa, we have a treat for you first. We have some archive footage of the Tarantula Nebula. We thought we would be able to share.
Super, yeah. So this Tarantula Nebula is the one I was talking about. So in the Magellanic Clouds, you have these nebulae, absolutely beautiful. So this is from the Sydney Observatory telescopes. That's right, isn't it, Catherine?
Yeah.
Yep, and not tonight, no luck tonight, but absolutely beautiful. And you can see all the structure, all the nebulosity. It's essentially gas that is glowing because of all the stars that are forming and shining inside the galaxy, inside the nebula. So nebula is just the Latin word for cloud, and that's what they thought it was. Now we know it's not really a cloud, but something very, very far away in space. Really, really cool structure.
Yeah.
It's very spidery, isn't it?
Yeah, you can see the arms there, and the nebula is so beautiful. We love looking at them. But to jump into our questions, Philip asks, where does gravity come from?
Well, there are a couple of explanations. Einstein tried to describe gravity and what it is, but also particle physics theory, tries to describe gravity in different ways. So really humans are now grappling through physics for explanations that are not just intuitive but mathematical, but also we can figure out whether they're true or not. We don't just want to explain how gravity works, but actually where it comes from. So you've either got the Higgs boson that you may have heard of, the idea that you've got this this force particle, this particle that essentially creates a force or you've got a Higgs field maybe that creates a force. So it's either described as a particle or a force field, essentially. You've got Newtonian gravity, which is a description of it as like magical action at a distance, and the laws describe how gravity works. And then you've got Einstein's description, which is, that mass and gravity are kind of space-time curvature, so that objects with mass curve space and time and create a gravitational field, but that doesn't fully explain how it actually comes about. The short answer is we don't yet know. And whether, you're talking about particle physics explanations or force field explanations, we don't yet have a full theory of physics and all the forces in it that are unified. So that's what theoretical physicists are looking for. And that's what we're looking for in the particle colliders as well. But a few years ago, the discovery of the Higgs boson was a real sort of a step forward in understanding that, fundamental particles, that you create when you smash atoms together and other smaller particles, really do exist, and you can measure them experimentally. So it seems to be something to do with tiny particles called bosons, but it's not the full picture yet.
Yeah, so many of these questions are at the edge of knowledge, which we love, so keep sending them through. One from Kathy, who's 10 years old, and she asks, what would happen to water if you poured it in space?
Oh, great question, Kathy. You can actually watch videos of this. It's fascinating. So right now there are quite a few, I think it's about 7 or 8 astronauts orbiting the Earth in the International Space Station. And what they are, because they're orbiting the Earth, they're constantly sort of falling towards the Earth, but they're moving sideways fast enough that they don't hit it. So that means that they do not experience gravitational force in the same way that we do when we're standing on Earth. So they're essentially what we call weightless, or they're in microgravity, if you want to be more correct about it. So they're floating around, they're enjoying themselves. When they want to drink water, they have to squeeze it out of a bottle. They squeeze it into the spaceship, and it creates a little sphere, a little ball of water, and it's held together by surface tension, and then they can drink the water, and they're kind of like floating balls of water. So that's how water behaves in space. It's very different. It's very cool. So maybe you and a grown-up can have a look on YouTube and have a look at some of that stuff. It's very, very exciting.
Amazing. One from Alan, who we enjoy seeing every month on our live streams, but he wants to know, where do gases come from that become the ingredients for new stars?
Yeah, essentially the Big Bang. So everything, chemically speaking, everything created in the Big Bang was pretty much just particles. When the universe expanded, it cooled down. And then those particles were able to get close enough together to be squished together by the strong and weak nuclear forces to create atoms. That stage of the universe where it cooled down enough to create atoms, created mainly hydrogen, a bit of helium, and then as gravity pulled things together, they were able to react together in chemical reactions in space to create the other small molecules of lithium created in the Big Bang as well. Essentially, all that was very basic molecules. And then when you recycle, you create a star, then it starts burning hydrogen to helium, and bigger stars create carbon and nitrogen and oxygen. And then when stars explode as supernovae, they create the higher up in the periodic table, heavier elements, and all chemistry is in stars. So basically, the light stuff's made in the Big Bang, the heavier stuff is made in stars, and the heavier elements made in stars spill out into space at the end of the star's life, creating the chemistry that we see in space. So all that stuff's been eaten and pooed out by a star, essentially.
Great. And one last question before we jump back into the remaining galaxies. But Kathy wants to know, what is at the center of our galaxy? Do we know?
Yeah, the center of our galaxy, we can see a couple of things. So we can see a bunch of stars that are orbiting what looks like nothing, like an empty space. We know that gravity works by, attracting heavy objects together. So there's this invisible heavy object in the middle of our galaxy, that is making these stars orbit. And by the laws of gravity, we can measure how heavy it must be, because we know how heavy the stars are, we know how far away they are, we know how fast they're rotating. So we use the laws of physics and Newton's gravity equations essentially to just figure out how heavy this invisible thing is. And it turns out it's 4 million times more massive than our sun. So that is a supermassive black hole at the center of our galaxy, and most galaxies have one. And actually, that really segues nicely into the next couple of galaxies, because we're going to have a look at some galaxies and the effect that galaxy collisions have on the supermassive black holes. So that is awesome.
Great. Well, let's take us there, Lisa.
Great. Well, let's have a look next to have a look at one of these really cool, so called active galaxies or active galactic nuclei. The nucleus is the center of the galaxy, just like the nucleus of an atom is the center of an atom. And what you're looking at here is one of the most massive, the largest, and the most luminous galaxies in our local universe, called Virgo A, unsurprisingly, in the constellation of Virgo. And it's really, really big. It's really heavy. It's got about 2 trillion times the mass of our sun. A trillion is 1,000 billion. So that's huge. It's 200 times more hefty than the Milky Way, even though the two galaxies are similar size. So this is what we call a supergiant galaxy. And not just that, a supergiant elliptical galaxy. What you notice when you look at it is it doesn't actually have any discernible shape. It's not flat like a spiral galaxy. It doesn't have spiral arms. It doesn't have a dust lane. It's just like it's an amorphous, smeary blob. And that's a technical term. And giant elliptical galaxies, we think, come about after a series of mergers between smaller spiral galaxies. So imagine 2 spiral galaxies crash together, and then another one joins in, and another one. Gravity's going absolutely ape and just ripping them apart. This is what happens at the end. You get this amorphous blob. Now, all those regulars of spiral galaxies that collided together each had a supermassive black hole at its center. So when the galaxies collide, the supermassive black holes are heavy, so they all sink to the middle. That's how gravity works. So they all actually collide and merge. So the supermassive black holes get bigger and bigger and bigger until you get something like this, a supermassive elliptical galaxy with a ginormous black hole. Now, for this galaxy, it's such a big black hole and it's so energetic that in 2019, which I'm sure you may have seen on the news, the first scientific observation of the event horizon of a black hole was announced, and it was the black hole in the middle of this very galaxy. So the Event Horizon Telescope was made up of over a dozen radio telescopes spread out around the world, observing at very high frequencies, above 230 megahertz, and they were tuned in to this Virgo A galaxy. Now, what they did was they took data from the galaxy, measuring radio waves, and they managed to put the images together using clever techniques, mathematics, using supercomputers, and smooth out the images. Now, this is the kind of science I've done for the whole of my career, using different radio telescopes. It's very clever. It's difficult to do, but those techniques are very, very smart. And they created a beautiful image. It looked like an orange donut of the gas that was created by the black hole ripping apart stars, which were falling into its gravitational mass hole. So this was absolutely amazing. The black hole was, candidate because it's very, 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 very big. And it's also creating a lot of action. It's eating a lot of stars and gas at the moment. And you can see that because there's this huge blue light coming out of the middle of the galaxy. You can see on the right-hand side this huge sort of blue jet. We call it a jet. And it's very, very high velocity. It's traveling at close to the speed of light. And it's visible in X-rays, radio waves, and light. Now, it's spraying out material from a hot region close to the supermassive black hole. And its supermassive black hole is huge. It's 6.5 billion times the mass of our sun. So this is really not material flying out of the black hole itself, because as we know, nothing can escape a black hole, but it's material around the black hole that is getting squeezed and stretched and pulled apart. And that region outside the black hole is what the image was taken with the Event Horizon Telescope. And it's also what's creating this jet. We think the jet is collimated, in other words, pushed into a straight line, into a narrow beam by magnetic fields. So this black hole is rotating, the stuff is rotating around, and magnetic fields along the North Pole and the South Pole of the black hole are shooting out material. Now, there's a lot more to happen with this galaxy. It's not the end for this galaxy, because it is growing and growing as time goes by. There are 50 or so other galaxies in its vicinity. So as we move through time, through the next few 100 million years, there is likely to be a lot more action where this comes from. Now, that's amazing. I mean, this galaxy is very, very exciting, and there's no shortage of galaxies like this. The next one I wanted to show you is quite similar. It has supermassive black holes, it has interactions, and it has amazing jets flying out of the center. But if we look at it just with a normal telescope, the Sydney Observatory optical telescope in the East Dome, this is what we see. It's called Centaurus A, and it looks like a lovely fuzzy cloud with a stripe down the center. So the fuzzy cloud part is made up of millions of stars, and it looks essentially like an elliptical galaxy with dust through the middle. But we know it can't be an elliptical galaxy because ellipticals don't typically have dust in them. So it's a bit of a mystery what's going on with this galaxy when it was just observed with regular telescopes like the ones at Sydney Observatory. So what we do is we look at different wavelengths again. And this image taken with different optical and radio telescopes from more modern observatories shows us the unusual and surprising shapes of this galaxy. So you can still see the stripe of dust that is absorbing the bright starlight from behind. But then above and below, you can see these huge dragon-like jets snorting out of the supermassive black holes region at the center of the galaxy. So Centaurus A is currently devouring a spiral galaxy. So this galaxy is the result of a collision, the merger of two galaxies, and an amazingly big, powerful black hole has created this enormous dragon-like jet. Now, we look at this galaxy in all different regions of the electromagnetic spectrum: infrared, optical, radio, X-ray, gamma rays. So it's the most extensively studied object in the southern sky. And the center of the galaxy is again what we call an active galactic nucleus. So we can see with radio waves right into the center of that galaxy. So as we see again, we are looking at the shape of the galaxy being changed by its history. Just a lot of, you older people, we've got more lines because we've been in the sun longer. Older galaxies, they've got, more features. They are either eating stars and ripping them apart, and they've got these jets, or they've got these dusty, dark lanes. The young, pretty galaxies, they are the spirals. The older ones, I think, have more character and wisdom. So the last one I wanted to show you tonight, and I will be really happy to have more questions after this one, is showing us what two spiral galaxies look like when they are colliding. And I'm particularly interested in this because, in fact, our own galaxy is not too long away from a collision, very much like this one. Now, these galaxies are called the antennae galaxies. Somebody thought they looked like the antennae of an insect, but they are a pair of interacting galaxies in the constellation of Corvus. So they're currently going through a big collision, two galaxies barreling together due to the force of gravity. And you can see the spiral arms have completely unfurled on the galaxy to the bottom. You can also see there's a lot of stuff going on. The blue color is kind of regular young stars that are just getting on with shining, but the older stars are the sort of orangey yellow regions. So you can see there's a lot of star formation happening at the top of the image. And that's due to the fact that the galaxies are colliding. Now, we're sitting in the Milky Way galaxy, as I said earlier, and we live in a local group of 50 or so small galaxies, some of which we've met tonight. The Magellanic Clouds are two. But we've also got a couple of big spirals near us, the Triangulum Galaxy and also the beautiful Andromeda Galaxy. So that's the nearby spiral galaxies to us. Now, when we observe the Andromeda Galaxy, we can actually measure its velocity and speed, and it's moving towards us incredibly quickly, 400,000 kilometers per hour. So when we fast forward that, we imagine the future. At that speed, it will take about 3.8 billion years until we collide with the Andromeda Galaxy. So this image you can see here, the antennae galaxies, this is our future. This is literally what the Milky Way will be like in around about 4 to 5 billion years as it's collided and a burst of new stars is forming. So at that time, our night sky will look very different. And it's fascinating to think about how the universe evolves in this way. Nothing is forever. Although our galaxy is currently a beautiful spiral galaxy, uninterrupted by such dramatic events we can see in the future, it will be very different. So this is the fate of our own Milky Way. I wanted to just mention that if you want to learn more about this incredible event, I did happen to write a book about it. So you can get When Galaxies Collide and learn all about the future of the night sky, and learn about also our connection to the night sky. Because for me, astronomy isn't just about using telescopes and looking at objects and learning using physics. That's an important part of it. But it's also about observing and also thinking about teaching younger people as well about astronomy. So that connection to reality is quite beautiful. So I would urge you after tonight, get inspired, get an app on your phone, and also go out and look for yourself, get some binoculars, a telescope, join your local astronomical society, or go to one of your local observatories. Hopefully, if you're in Sydney, you can pop up and see this amazing team and see what's going on. So with that, I'd love to have your questions again, and hopefully we can explore some more mysteries together. Thank you.
Thank you so much, Lisa. And we do have a lot of active questions in the comments. First one from FJ, why do galaxies collide?
It's all down to gravity. Gravity is a cool force because it's unlike the other forces. Most of the other forces that are long distance forces, like electromagnetic forces, they can be attractive or they can be repulsive. Like two magnets, north and south, attract, but north and north repel. They push against each other, and south repel. So gravity is a force that is a long distance force. Wherever you are in the universe, you're attracting every other particle, every other being, every other body in the universe, just with a very small force. And also, it's always attractive. There is no repellent part of gravity, not that we know of. So it's very attractive, it's very powerful, and it essentially assembles everything in the universe. And it creates the galaxy clusters that we know, and it creates our solar system as we know it. So we owe our life to gravity, we really do, not just for sticking down to the ground here on Earth, but for absolutely everything. Thanks, gravity.
One from Peter, he asks, the images that we've been looking at, how have they been captured? Are they actual telescope images? Are they artist impressions?
Yep, they're all real telescope images, everything you've seen tonight. And many of them have been taken with NASA's space telescopes or the European Space Agency's missions. A lot of them from the Hubble Space Telescope as well. But there are also elements from radio telescopes and then things like the infrared Spitzer Space Telescope. So lots of different things melded together. So they are all real. They're not artist impressions. Real life is so cool.
LJ asks, how do you estimate the age of a galaxy?
Hi, LJ, my friend LJ. You can estimate the age of a galaxy from its characteristics. So a lot of it can be done with nearby galaxies from the age of the globular clusters. So the oldest thing in the galaxy generally are the stars in the globular clusters. So you can figure out how old it is from that. There's chemical ways, there's ways that kind of make general assumptions about the mass in a galaxy and the size of the black holes. There's a few different ways, and we compare those different ways and get a bit of a handle on it, but it's not an exact science. You basically, the simple way is find the oldest star, and that's how old the galaxy is.
Ken and his son Atticus, they'd like to know when is the best time to view these galaxies?
Yep, it depends. A lot are in Virgo, so great time is now, and great time is winter because it depends where they are in the sky, but most of them are up now. So good time for the Magellanic Clouds as well. If you're in different parts of the country have slightly different, subtle differences, but winter is generally the best time for a lot of these galaxies in Virgo. And if you're not sure, type into your app on your phone the name of the galaxy. Normally the M something name is the simplest, and it will show you where it is in the sky. It's just above the horizon. So that's really handy as well. That's probably the best way to actually find them because the constellations are quite big, so it can be a bit complex.
One from Daryl asks, Lisa, can you describe what a quasar is?
Yeah. Quasar stands for quasi-stellar radio source. That was the name that was coined a lot of years ago, decades ago, when they were first discovered using radio telescopes. In fact, one of the first discoveries of quasars happened at Dover Heights, just near North Bondi, on the cliffs there, which is where one of the first CSIRO radio telescopes was. A very cool history there if you ever visit and have a look at the little plaque and the history. But quasars are radio galaxies like the Centaurus A1 that we saw and like the Virgo A. So they look like the dragon fire-breathing kind of galaxies. They've got active centers, active nuclei. And what that means is really a supermassive black hole is sitting there eating stuff. And it's eating gas and stars and ripping apart stars and devouring the gas. And what happens then is the gas, as it sort of get pulled towards the black hole, starts spinning around the black hole and around in a disk. It gets very hot due to friction. And then the hot, the emission from that is sort of flown up and down through the magnetic fields of that region. So some of the energy flies out. So that is a quasar. It's a galaxy that's devouring stars, and in the black hole, it's flinging out radiation, flinging out energy and particles along the north and south poles of the magnetic field. And we see them all over the universe. They're very helpful to enable us to study where black holes are eating things and also how galaxies merge and how that's happened throughout the history of the universe.
Amazing. And one last question from Annie Rose, and asking this knowing that there's a lot of aspiring astrophysicists watching tonight too, but she asks, did you study in Sydney to become an astrophysicist? What was your journey?
Yeah. Just a brief journey. So I was 12 when I started to get interested in astronomy. I just looked at the night sky and it was with my dad, and we saw Mars and we saw the constellations. I'm from England originally, so we saw the Plough and the northern constellations. We saw Orion the other way up, and lots of cool constellations like the North Pole Star with the little bear hanging off it, and there's all different constellations up there. But it was a journey then through reading a million books, finding out, going to my local astronomy club, looking through telescopes that they had there, and learning and going to the planetarium and the museums, and then studying physics. I studied in the UK, and I did a master's degree in astronomy and astrophysics at the University of Newcastle in England, and then a PhD in radio astronomy. And a PhD is a doctoral degree. It's essentially a research degree you do for 3 years after your regular degree. And you learn how to be a scientist. You learn how to use telescopes, giant, massive ones, and at the University of Manchester. So it was great fun, hard work like everything, and really good fun. And I really feel very fortunate to still work in astronomy and still be involved in research. So it's been amazing.
And well, that wraps up our presentation tonight. Thank you so much,
Awesome.
Lisa. Thank you,
I
everyone,
always love it,
for
Catherine.
watching.
Thanks, everyone.
It's always a pleasure, and we'll have you back in September, which we're really looking forward to. Thank you, everyone, for joining us. We hope to see you next month. And Lisa, is there anything you'd like to say or end on?
Just always love working with Sydney Observatory. Keep looking up. Download your app, Skyview, Sky Guide. There's lots of them. And you can even lay in bed and imagine you're looking at the stars. It's such fun.
Well, I think we'll do that tonight. So thank you, everyone.
Thanks,
Bye.
everyone. Bye.